Welcome to a video of the Fourier Transform exercises handset or handout. In this first exercise, exercise 0 in your handout, we will use the Fourier Transform to solve a differential equation. This is a typical application which is very useful of the Fourier Transform, and this is a good exercise to practice it. So in this case, they give to us differential equation, as you can see over here, and they ask us to calculate the impulse response of an LTI system which has an input-output relationship determined by this relation. In other words, by this differential equation. In other words, what we have is a LTI system, linear time invariant system, with an input x of t and an output y of t, and the relation between the x and the y is exactly this differential equation. However, you know that another way to express in LTI systems the input-output relationship is by using the impulse response, which is h of t. H of t is the output that I get when the input is a delta function. Okay, so let's go ahead and do that. So the first thing that we need to do is to do a Fourier transform of this equation over here, the full differential equation. And for that, we just remember the relationship or the parent transforms between a signal xt, which has a Fourier transform x of omega, and the differential, the derivative of x of t, which has a Fourier transform which is j omega x omega. And if this differentiation or derivative is not the first derivative, but if it is an, let's say, an n derivative, okay, then we just go ahead and put an n over here and everything will be just right. So as you can see, the Fourier transform is very useful because it moves from derivatives to equations which do not have any derivative at all. And this is exactly the reason why it's a good tool to solve differential equations. So in this case, we go term by term and we just Fourier transform all the equation. So the first term that we have is this one, which is the second derivative of y with respect to time two times. So it will translate into y square omega square times y omega, which is a Fourier transform of y. The second term, which is this y, will be 4 times the first derivative, so it's j omega times y omega, plus this term, which is 3 times y, so it will be 3 times the Fourier transform of y of t, which is y capital Y omega, and this is equal to the derivative of x with respect to t, which will be j omega capital X with capital X of omega being the Fourier transform of x of t, plus 2 times x of t, which will be 2 times capital X of omega. So you can see that we have Fourier transformed a differential equation and it converts, or it translates in a algebraic equation in the variables y and x, but in its Fourier transforms. So what we need to do, and in this exercise they are asking, is calculating h of t. H of t, you know, it has a Fourier transform which we call h of capital H of omega, which is the frequency response of the system, and this is exactly the relationship between the output capital Y divided by the input, which is capital X of omega. So what we need to do is, in this algebraic equation, we need to take apart capital Y divided by capital X, which is very easy because, again, this is an algebraic equation. So if we factorize all the y's together, all the x together, and we separate, what we get is h of omega, which again is just getting the capital Y divided by the capital X in the above equation, and you will get this 2 plus j omega, and in the denominator we will have j omega squared plus 4 times j omega plus 3. Okay, so this will be the frequency response of the system. But what they are asking us is of h of t, and to get h of t we need to do the inverse Fourier transform of this expression over here. So in order to do that, we need to do first two things. We need to firstly do a factorization of the denominators, which means that the numerator is just the same, and the denominator we just divide this polynomial in a factor of 2, which the first one will be 1 times j omega, and the second will be 3 plus j omega. I won't go into the details of how do you do that, but it's very, very easy. You can do, for example, j omega, just not to get confused, you call it x, and you end up with an equation in the denominator, which is a square equation, which will be x squared plus 4 times x plus 3, and you equal to 0, and you get the roots of this equation, which will be x equal to minus 3 and x equal to minus 1. So you can express and say that this is x minus one of the roots, for example minus 1, so it would be x plus 1, and the other x minus the second root, which is minus 3, so you will get x plus 3. And then you can go ahead and just call x j omega, and you will get j omega plus 1 times j omega plus 3, which is what we got above, as you can see. Okay, so very, very easy. Okay, so now we have the denominator factorized. So the next step that we need to do is divide this equation in a sum of two fractions. So divide in simple fractions. Also, this is very easy. You have done that in the previously in other courses. If you divide it into fractions, you will get the first fraction in the first denominator, which is 1 plus j omega, and the numerator is 1/2. And the second fraction will be another 1/2. 1 divided by 2, and in the denominator is 3 plus j omega. Again, I won't go into the details on how do we do that, just a brief reminder. You just go ahead and you equate again j omega, just to not get confused, to x, and you will get an equation which is what you need to divide into fractions will be this 1 plus x times 3 plus x. Okay, and what you want is to divide this into fraction. The first fraction has a number a in the numerator and 1 plus x in the denominator, and the other fraction has a b in the numerator and 3 plus x in the denominator. Sorry, this is a b. And you just multiply terms here, and you equate 2 plus x to a times 3 plus x plus b times 1 plus x. And here is a matter of giving values to cancel each of these terms independently. So for example, if we put the value x equal to minus 3, the equation will translate into 2 plus minus 3 equal to a times 0 plus b times 1 minus 3, and from here you get the value a, which is 1 divided by 2, and if you put the value x equal to minus 1, from the same you will get 2 plus minus 1 equal to a times 3 minus 1 plus b times 0, and here you also will get b equal to 1 divided by 2. Okay, so that's how, remember that this is a very simple case on how we can get the numerators. Okay, Well, we are almost done to get the inverse Fourier transform. We just recall that there is a pair of Fourier transform, which is the following one. The exponential of minus at u of t, this has a Fourier transform which is 1 divided by a plus j omega. Remember that if this is true, if omega is complex, then the real part of a has to be positive. Okay, so in this case, as you can see, we have two terms which really look like this. So it's immediate to get the h of t, which again is just doing the inverse Fourier transform of h of omega, which is what we have over here. So it will be the inverse Fourier transform of 1 divided by 2, 1 plus j omega, plus 1 divided by 2, 3 plus j omega. And again, applying this pair transform, what we get is the first term will be 1 divided by 2, e2 minus t, u of t, and the second term will be also 1 divided by 2, but in this case it will be e2 minus 3t of u of t. Okay, so this is the impulse response of the system defined by this differential equation. Okay. I just also make a quick reminder, how do we get these Fourier transform pairs? Okay, also very easy, we just apply the definition, the Fourier transform of e to minus at u of t. So we apply the definition. The definition, it will be the integration between 0 and plus infinite, and we put here a 0 because we have a u dt. So here e to minus at times a to minus j omega t dt. And this is immediate because if we get everything in the same exponential, what you get is minus a times j omega t dt, which is immediate. This is minus 1 divided by a plus j omega, and then it's the same exponential, a minus a plus j omega t between 0 and infinite. And this, if you calculate it, is exactly 1 divided by a plus j omega, with the only consideration that the infinite goes to 0, the a to minus a j omega t, if the real part of a is positive. Only in this case the result is this, if this is only real if the real part of a is positive. Okay, so yeah, brief summary on the how to do the Fourier transform of this exponential that has allowed us to calculate h of t, the impulse response of the input-output relationship given by this differential equation. Okay, so if instead of solving this problem to get h of t, they had asked us to solve it to get y of t given a certain x of t, it's also very easy. We just, instead of getting y divided by x, we just separate y as a function of x and Fourier transform inverse, which will be tantamount of getting the differential equation solved. But in this case, they were not asking us that, but to get the impulse response of the system. I hope it's clear. Thank you for your attention and see you in another video. Bye-bye.